What up, y'all? Close this. Close this. Oops, can't navigate away. All right. Wow. The latency is 22 seconds. That's a lot. Better than lagging, though. Buffering. Joey, what's up? Slowest timer in the world. Starting the timer is like the longest minute of my life. I sit there and wait to click the start button until the next minute clicks. And I swear to God, those are the longest minutes. Oh, my phone alarm's gonna go off too. All right, let's do this. So, we are on lecture 6. We're doing everything that you need for task 4 right now. Before we really get into it, quizzes. Gerline has classes 1 graded, but I want to just take a quick look at everything before posting to Autolab. So after lecture, I'll be posting that, and she should be done with data structures 1 as well after that. So after lecture, I'd say probably at least an hour after lecture, and depends how busy office hours is, so maybe 2 hours after lecture, we should have quizzes posted to Autolab, quiz results posted to Autolab at that time. So no quizzes quite yet, but they will be out today. So everything we learned today is prepping you for programming task 4. And I have to warn you, there is a jump up in difficulty from programming tasks 1, 2, and 3 to task 4. In my opinion, task 4 is where we finally get into the level of rigor that will be at for the rest of the semester. So task 4 is quite a bit of a jump up. If you've heard anything about last semester, task 4 was absolutely horrendous. It hit the whole class, took everybody by storm. I did refactor a bit. I did change the structure of tasks 4 and 5. I took what used to be 4 and put it into what used to be 5 and 6 and spread out the workload a little bit, because 4 last semester was really hard. 5 and 6 were a bit too easy, so I spread out the difficulty a little bit. So hopefully that helps out. I think it will. The way task 4 was structured last time. But anyway, if you haven't heard about that, which most of you haven't, just disregard. But still, it's not as bad as it was, but still there is a big jump up in difficulty from 2 and 3 to 4. This is more of the flavor of task 1, where you are writing your tests and code. So you've got a break from writing tests in tasks 2 and 3. In task 4, you're back to writing testing and code, and there is quite a bit of stuff. There's just a lot of stuff to do. Even the description is, it's just a lot of words, just a lot to comprehend. So more so than the previous 3 tasks, make sure you're starting this one early, going through it. I maintain that there's nothing overly difficult in here. There's just a lot of it. So just make sure you start early. Make sure you give yourself plenty of time to get this one done, especially if you're going for the expected deadlines like you all should be going for. You should all be going for those. But make sure you start this one early to be able to finish it by next week. So what is this homework about? It's about inheritance. Let's do it. Let me get all 3 of these open in tabs in the right order. Download it. to prove that what I'm presenting from, not to prove, but to verify mostly for myself in case I made a mistake, that what I'm presenting from is identical to what you have access to. So you have access to these exact slides that I'm using. Typos and all, there are. I just noticed a few typos as I was looking over these slides this morning, but I didn't fix them. I'll just point them out and say, look, I made a mistake. All right, inheritance. So let's learn inheritance through an example. So suppose we're making a game and we want a player that moves around the world and interacts with two different types of objects. I gotta tilt my monitor here. And interacts with two different types of objects, health potions and weapons. So you have to use some imagination here because we're not actually building this game. But a player who can possess, it's not really the right word, but have health potions and weapons in their inventory and then use these items and have it affect the way the player, the state of the player in the game. So that's what we want to build. So let's start with a health potion. Let's build a health potion class. We've seen how to build classes usually a long time ago, but in the summer class it was just last week. We saw how to create classes just 9 days ago. But you also should be studying a lot more each week, so you should be quite familiar with how classes work. Of course, I have glanced at the quiz results. I'm not 100% positive that's a true statement, unfortunately. But at least half of you are very familiar with how classes work. So let's just do a little bit of review on how they work. With the health potion class, we're going to create the health potion class, give it some instance variables, give it a constructor, give it state and behavior. We have state in the form of instance variables, a constructor to initialize those variables, and some behavior, a method that just prints something to the screen for now. We're not doing anything too fancy. We're just trying to lead up to the concept of inheritance. So if you use a potion, we're just going to print to the screen that a health potion was used, and this increased variable is the amount of hit points that are going to be increased when the potion is used. So it's going to heal the player by that many points of health. Cool. But like I said, that's all review. We all know how to do that. If you don't, go back and review. I don't really have time to do more review than what I just did. So we got to move on to the next thing. What's the next thing we're going to learn? Inheritance. Woo! The name of the lecture. Hopefully you were aware that this is the inheritance lecture. But this is what we want to learn. So let's dive right into it. This is inheritance. This right here, what's on screen, is inheritance. So let's talk about what is even going on here and how this works. What inheritance is, how it works, how to use it, how to write code that uses inheritance. So instead of just writing the health potion class like we did and putting everything in the health potion class, all of its state and behavior, instead we're going to inherit some state and behavior from another class. So we're going to create this game item class, which is going to have all of the code, all of the state and behavior, all of the instance variables and methods that are common to any item in our game. Which right now it's just health potion, but it will eventually be weapon and any other item that we can think of. This is where all the common code should go. And just thinking through how our game works, I think every game item in our game should have a location in the game world. So we're going to have some X location, some Y location, which used to be in the health potion class, along with its amount of health increased. But now we're going to put this X location and Y location in the game item class to say every game item in our game has a location in this XY space. We're going to assume this is a two-dimensional game. So maybe it's a game with an overhead view where you're looking down on your player on a 2D grid that's representing the game world. And each game item has some 2D location in that space. And then the constructor, which initializes that location. And eventually, it's not on screen yet, but eventually we'll have a move method that allows these game items to move around in the game world. Because right now we have two private instance variables. They can't be accessed from outside the game item class, and they're not used at all inside the game item class. So these are two useless variables to have in the condition that the code is in right now. But eventually we'll have a move method a public move method, which will take care of that. which actually gives some functionality here. And then we're going to say extends game item. This is where we start applying inheritance to our code. So the concept of inheritance, we're going to have a health potion that inherits from game item. In our code, the keyword is extends. Health potion extends game item is read as health potion inherits from game item. And what this means is that health potion is going to gain or absorb or inherit all of the state and behavior defined in the game item class. So instead of defining all of the state and behavior inside the health potion class, how we used to declare X location and Y location right here inside the health potion class, now instead we're inheriting those two instance variables from the game item class. The game item class has instance variables X location and Y location. And since health potion extends game item, health potion does have instance variables X location, Y location, in addition to its own instance variable increase, because it inherits them from game item. So we get the state and behavior, all of the state and behavior defined in this class, this game item class, is inherited by health potion. So this is the same thing as saying health potion, putting these two variables right here without the extends, putting those two variables right here, and then instead of having this, which we'll talk about in a second, the super constructor call, having these two lines of code right here. That'd be the same thing. I think there are some technical differences to what with what I just said, but it's mostly the same thing. At least for this example, it is the same thing. So we inherited all the state and behavior, which the behavior is just the constructor for now, but any methods in here as well would be inherited by the health potion class. So we get, I got ahead of my slide already. We get the constructor, so we have access to this constructor as part of the behavior of the class that we extended or inherited from. And we can call that constructor using this super constructor call. A little bit of vocab. The game item is said to be the superclass of health potion or the parent class. There's two. This is so often in really anything, but computer science included, where we have one concept, one thing that has two or more different sets of vocab. So we can say superclass or parent class, and health potion is the child class or the subclass. I wish one of those sets of vocab would just go away and we could just stick with one. I'll usually stick to super and subclass. I should update the slide to have subclass explicitly on here. But super and subclass, but if you catch me saying parent and child class, sometimes I do end up using that vocab too. So I'm part of the problem. I mix them as well. Maybe I should just present one of them and pretend the other one doesn't exist. And then eventually everyone will forget that parent and child class exists. And the superclass constructor, since we do inherit that superclass constructor, or actually not since we inherit it, but whenever you extend a class like this, and this is one of the first big takeaways here, the whole concept is a big takeaway, just knowing what inheritance is. But this is one of the first big takeaways that's easy to miss. This is a common mistake that students make, so I'll mention this like 5 times throughout this lecture. The superclass constructor must be called in the inheriting class. So health potion extends game item. That means in the health potion constructor, when the health potion constructor is called, the superclass constructor, which is game item in this case, its constructor must be called. It has to be called. There's no getting around this. It has to be called. The superclass constructor has to be called. So if you're creating an object of some type that extends another type, that type that it extends, its constructor must be called when the health potion constructor is called. Now to foreshadow a little bit, you don't always have to call it explicitly So you don't always have to call it in your code, but it does always have to be called. So a slight, subtle semantic difference there that I'll talk about later in like a slide or two. So not too much later. But this must be called. So the syntax for this is super. That's kind of a reference to the super class. It's not a reference to an object. So the syntax is a little strange here. It's kind of like saying game item here. But we don't say game item to call the constructor, even though that is the constructor, the name of the method that we're calling. We use this special variable, this keyword super, to refer to the super class. So we say super, and then just like this super was game item, we're going to call the constructor just like that, importantly without the keyword new. So this is one case where we call a constructor without the keyword new. Very importantly. If you put new here, I'm pretty sure you just get a compiler error, and IntelliJ just won't let you do it anyway. But it's important to know why that is the case, and we'll talk about that when we get to the memory diagram in more depth. The short answer is there's only one object that's being created. You don't want to create another new object inside a constructor, because your constructor is always already constructing the object. You don't want to create another new object. You're creating one object that benefits from two constructors. Well, if there are multiple constructors, you only have to call one of them, just one. But one of them has to be called. If there are multiple, you would pick which one you want to call. So we're calling it with the same syntax as we would, just without the new keyword, and super in place of the name of the class. And then we're forwarding, we have some parameters here. So we're forwarding this X location, Y location from this constructor's parameter list and forwarding it to the next constructor, because the next constructor is the one that's actually going to use those variables. This constructor only takes X location, Y location, simply to forward them those values to the next constructor, to the super constructor. If your super constructor, no problem. If your super constructor takes parameters, this call must be explicit, as opposed to a constructor. This isn't the way we're going to see the code, but just for the sake of this example in this slide, if your superclass is constructor does not take any parameters, then you can leave out that line in your code, but that super constructor is still called. The super constructor must always be called. But if it takes no parameters, you don't have to explicitly call it in your code. This is implicit. Java just says, oh yeah, I assume you want to call that super constructor because you don't have a choice. I didn't give you a choice. Speaking as Java, Java didn't give you a choice whether or not to call the super constructor. It must be called. So it just assumes that you want to call it, and you don't have to say anything in your code. You can put super with an empty parentheses. You can put this in your code as the first line of your constructor, but it's optional to explicitly put that call in there, and Java will implicitly call the constructor, but the constructor, superclass constructor, is still called in this case. So if you've done Java before, if you did AP computer science or anything, you might have seen this before where you don't have an explicit superconstructor call, but the superconstructor is still called. It's just implicit, and Java does it for you. It is still called. The reason that's going to be important is in your memory diagrams, knowing that if you get code like this, that you have another stack frame for this constructor call going on your stack. That's going to be the big thing, the big way I'm going to assess whether you understand superconstructor calls or not. Just so you know. All right, but why? Why do this? We just talked about inheritance for a bit. I introduced what inheritance is. You're inheriting the state and behavior from another class into your class, and you have to call the superclass constructor. If you're using inheritance, that superclass constructor has to be called. That's what we just learned, but why bother? Why did we even bother with this? Because the first example I showed where all the code was in the health potion class and there was no inheritance, that was simpler. than learning inheritance? Why are we learning a new concept to make things more complicated and to split our code into multiple classes? And by the way, each class will be its own file. So now we have a project with 2 files where there used to be 1. We're just adding complexity here to get the same goal, to meet the same goal, get the same functionality out of our code. So why are we doing... Oops, I forgot to move my face. So why are we doing this? Well, the advantage comes from when we have more classes. So when we have more game items in our game, and here's where our weapon is going to come in, this is where we get to see some of the benefits of inheritance. So we have this class game item, which is going to have all the code that's common to all of our game items. And that doesn't make sense when we only have one game item, because just put everything in health potion. That's the answer. That's the right way to do it. But if we have multiple game items, now we have one game item class which handles all of our location-based stuff and anything else that we want a game item, every game item to be able to do or have in its state and behavior. But we have 2 separate types of game item that both extend game item, and now we're cutting that location code out of both of these classes and making these classes simpler to write, because most of the, not most in this case, but a lot of the code that they have is just inherited from game item, which we only write one time. We write game item one time, and now we benefit from that game item code twice. Now we could cut and paste code, cut and paste all this stuff into each of these and say, you know what, that's fine too. I'll just cut and paste, everything's good. Which is still, okay in this example with just two classes. Maybe that's fine. Maybe that's okay. But things are going to get more complex. As you actually build out this game, things are going to get more and more complicated. You're going to have more and more features in your game. We're going to have that move method that I promised earlier, which is going to take your dx and dy and move this item to a new location. And now both weapon and health potion inherit the move method, so we can call a move from objects of type weapon or health potion because they both extend game item, which is a bit cleaner. Sure, you can still cut and paste, cut, paste, paste, but 2 things, 2 big reasons why we don't want to do that in general in our code. One, what happens when we have hundreds of game items? I don't want to cut and paste that code in all 100. But even then, you might say, well, each time I create a new class, I got a bit of work to do anyway. Well, it's a big deal if I add 1 step to the creation of a new game item. And you know what? Somewhat fair. But the second point is going to be the big killer, the one that's going to bite you. You got 100 different game items. You got different types of weapons. You got health potions and mana potions and traps that you can set, all kinds of things that you can store in your inventory, relics, all kinds of stuff that you might have in your inventory as a player, or just in your game world in general, different things you might have in your game. And you have this code and some other code copied into all 100 of those or hundreds of them. And the big second point is, what happens when you want to make an update? What happens when you want to change something about the way game items behave in your class? Maybe I want to change this to a 3-dimensional game and add Y location and have things being able to be thrown in a nice parabola. You're going to have to go to every single one of those classes and update that code, which you're going to update it once and then cut once and then paste hundreds of times, which is pretty painful, and it's very susceptible to human error. You're going to miss one of those classes, and one of your game items is still going to be behaving in a 2-dimensional way instead of the new 3-dimensional way. And you're going to have some really, really frustrating bugs in your code. And if your users find out before you do, you're going to have some silly videos on the internet about your game glitching out and being really crappy. We want to avoid the potential for making those types of mistakes. So instead, we put that code one time in game item. We have hundreds of classes that extend game item, and we want to change every game item in our entire game to work in 3 dimensions instead of 2. We write that code one single time in game item. We update our code here, and then every single class that extends game item automatically gets that update. Gets that change, that new behavior is just automatically everywhere, and you only had to change the code in one place, one time. You only have to test it once. You test the game item class, and then you know that it works in every class. Same thing if you want to add a whole new method to every single game item. I would add that method to the game item class, and every game item, everything that extends game item, automatically just gets that method without having to go to each one of those classes and update them manually. So that's the big benefit of inheritance. When we have lots of classes that extend a single class, we can update that one single class and have that change all of the classes that extend it. That's where we get the real power of inheritance, and that's a reason to set up inheritance in the first place and learn inheritance in the first place. The next big reason, we'll have to wait a little bit to see. We'll have to wait a week and a half. But polymorphism, in my opinion, is the even bigger payoff to inheritance. Polymorphism gives us a lot of power, and we can't use that without inheritance. So a little foreshadowing, we're not talking about that today, except very briefly at the end of this lecture. I'll be like, polymorphism, by the way. But to get the full power of polymorphism, we'll have to wait. But for now, this is the big payoff, updating lots of classes by changing code in one place. So it's kind of extending the idea of writing a function or a method. You write that code once, you call it from a lot of different places, and if you update that function or method, it's going to change the behavior of all of those methods throughout your whole program. Same idea, except we're elevating that to the level of classes. We update one class and change the state and behavior of all classes. Can you inherit multiple classes? No, you cannot. So when we get to polymorphism, I'm going to introduce something called interfaces, and you can extend, or rather implement, the vocab gets a little different. I guess it's still inherit though. You can inherit multiple interfaces, but not multiple classes. You can only extend one single class. So if you have a situation where you want to extend multiple of them, only one of the things you want to extend can be a class, and the others you might want to refactor your code to make sure that they're interfaces. Interfaces, I'm getting a little off topic, but I do want to mention, interfaces are, oh no, it's way off topic. If this line doesn't make sense to you, don't worry, we're going to talk about it in a week and a half. An interface is like a class, except it cannot have instance variables, and it can't have non-abstract methods, which means all of its methods can't have definitions. Its methods won't have bodies to them. Then you can extend multiple things. Based on everything that's covered in the class right now, the short answer is no, you can't extend multiple classes. Actually, with the word classes, that's just absolutely true. Forever. In Java, anyway. Some languages let you extend multiple classes, but we're a little off topic, so let's get back to it. Let's go through this code, trace through, and do a memory diagram. A lot of this memory diagram will be old hat. It'll be stuff that we've seen already. But there's two big things we want to note. One, this is the second time that I'm talking about the superclass constructor. Superclass constructor will be called when you create a new object of a type that extends another type. The superclass constructor will be called. That means we have to put that frame on the stack. So when we create one object, we're creating one weapon. That's going to put the weapon constructor on the stack, as we've already seen. But then it's going to call the superclass constructor and put the superclass constructor on the stack. So we're going to get two stack frames, two constructor stack frames to create one single object. Let me move my face again. I'm going to hang out in this little zone right here. I can get a little bigger. This is my little happy place right here for this memory diagram. So that superclass constructor is going to be called, and when a method is called, which method definition do we use? So here we're going to call use from a weapon, That's just normal stuff. We've seen that plenty of times. We go to the weapon class, we find the use method, but we're going to call move through an object of type weapon, which weapon doesn't have a move method. So we can see that it's going to go to the superclass, find the move method, and call the inherited move method, because it did inherit that method from the game item class. So that's the method that's going to be called when we call move. So we have a method being called from an object of a type where that class doesn't define that method, but everything's fine because of inheritance. We inherited move from game item. So those are the two big things that I want to highlight throughout this memory diagram. So let's get on with it. The first part, stuff we know already. We're saying new weapon. We have these three arguments, which are going to be assigned to these three parameters. So we have our parameters on the stack inside the weapon constructor stack frame. This is a reference to the object being created. So whenever we say new weapon, we're going to create a weapon on the heap. Right now it's empty for now, but we're going to, of course, add to it in the next slide. Picking a random number, I was feeling 350 when I made the slide, so I just chose OX350. And this is a reference to that object being created. I already said that, but worth repeating anyway. Then the instance variables. So when we create an object, we get all of the instance variables of that class matching the type of that object, but we also get all of the instance variables of any classes that it extends. So we do inherit all state and behavior. State are the instance variables, behavior is the methods. So we inherit the state of the game item class, which are the two instance variables, X location and Y location. So when we create this weapon on the heap, it doesn't just have the damage instance variable, it also has X location and Y location, which it inherited from game item. So we inherited the state from the game item class, and that state was in the form of X location and Y location instance variables. So as the first big difference, we get the instance variables from the superclass. The next big difference, and the one that students miss a lot, they've been missing it less often since I say it so many times in my slides now, but some of you will still forget this on your quiz, next week, right? It's just next Thursday, a week from now. Man, this flies. Is the super constructor call. So here's the second time I mention it, third time I mention in this lecture. The super constructor call. We're calling a method here, and we're calling a method that we have the code to, as opposed to like the print line method. We don't have the code to that. It's internal to Java. We're not worried about it. But this method call here, we do have the code. It's going on our memory diagram. We're adding a stack frame for that super constructor call. We are calling the game item constructor. It goes on the stack. It goes in its new stack frame. And I don't think I mentioned this yet. I don't know if we had a method that called another method yet. Maybe we did. I don't remember. If we didn't, here it is. And it's going to happen a lot in one of the later memory diagrams this lecture. But stack frames never go inside other stack frames. Since this method called another stack frame was created, but stack frames are never inside each other. The next stack frame you create always goes below the lowest stack frame. It gets pushed to the top of the stack. So it's completely separate. It's its own separate thing. And now the game item is on the top of the stack, and this is the active stack frame now. The weapon is completely what we say out of scope. It can't be accessed right now because it's not on the top of the stack. Only the top of the stack can be accessed, and we can only push and pop from a stack. So we get the game item constructor on the stack and pass those X location, Y location to this constructor. It gets its own copy of its parameters on the stack inside its stack frame, and then it's going to assign those variables. This inside the superclass constructor call is also a reference to the object being created. So we have two constructor calls on the stack. Only one of those constructors was called using new. So there's only one object being created. When we say new weapon, we're creating an object of type weapon. We're not saying new super. We're not creating a new object here. We're calling a constructor for an object that's already partially created. So this is going to be a reference to that object that we're creating, the single object that we're creating with these two constructor calls. Two constructors working together to construct a single object. So this is a reference to that single object that's being created. So this dot x location equals x location. X location, we go back to the stack frame. We always start in the stack frame to resolve an expression. X location 3.9. So this dot x location gets the value 3.9. Same with y location. That stack frame ends. We hit the closing brace, and we set damage. This dot damage equals damage. So damage gets the value 10. That stack frame ends, and we have one object fully constructed, and we can store that reference in the weapon variable in the main stack frame. So new, this expression, new in a constructor call, resolves to a reference to the object that was created, and that's what's assigned to weapon. So OX350 is what's stored in the weapon variable, a reference to this object that was created through these two constructor calls. And that's a lot of what your inheritance memory diagram is going to be. The next thing is what method is going to be called, which is the next thing we'll get into with use and move. But this is a lot of it, just making sure you get that super constructor call on the stack. And all the other little things, like making sure these inherited variables are part of that object. Little things like that as well that we talked about. But the big thing, this is one of them we can grade at a glance. If I am grading this and I see a weapon stack frame but no game item stack frame, done. You didn't get it. That's why I say this so many times in lecture. It's super important that you understand that. And if you don't understand it, it's an auto fail on that quiz. It's pretty fundamental. There's only two real takeaways for your quiz, for your memory diagrams when it comes to inheritance. The super constructor call and which method is going to be called when we call a method. So that's one of them. Super constructor call. Don't forget it. Do not forget that. All right, now let's get into the what method is going to be called when we call a method. I think that was 4. I said 5. I was just guessing how many times I mentioned it. That's 4. I know there's at least one more coming up in a future memory diagram. But don't forget your super constructor call. So weapon.use, we're going to call this method. And how do we know which method to call? Well, in this example, there's only one use method and one move method. So even if you completely miss the point here, you'll still get the right method. But that won't always be the case, and it won't be the case in the next memory diagram. So let's just warm up to this on how to do this. Weapon.use, the big thing here, is that we're going to look in the class matching the object type. I guess that's not really the big thing. We've done that already to warm you up to this when we talked about classes. But weapon.use, the object that is the calling object is of type weapon. So we're going to look in the weapon class for a method named use. So this is our strategy. This is our progression as we're looking for the method that's being called. And we actually do find it here, so our search is over. We find the use method in the weapon class when we call the method through an object of type weapon. Search is over. Everybody can go home. We found the method to call, and then it's a matter of calling the method. Calling object is OX350. Again, in this example, there's only one object, so you can't get that wrong. If you get that wrong, that's definitely an auto fail. There's only one object. You can't pick the wrong one. And then it prints to the screen. La-di-da. Yay. Damage dealt equals this dot damage, 10. Okay. So now let's get to the more interesting one. Weapon.move. Now we do the same thing. We're going to do weapon dot move, we're going to call the move method through an object of type weapon. So we look in the weapon class for a method named move, and holy crap, there's no method named move here. What do we do? And here the search is going to continue to the superclass. So if we don't find the method that we're looking for, then and only then do we go to the superclass and say, hey, game item, y'all got a move method for me? We go to the game item class and look for a move method that takes 2 doubles, and we do actually find a move method that takes 2 doubles, and now we have the method that we can call. So we're going to look for the method in the class matching the object type, the calling object type. If we don't find it, then we go to the superclass and continue our progressions. We find it in the superclass, so we're happy. If we ever get through all our progressions and don't find the method, well, that's a compiler error. Your code doesn't compile, your code doesn't run. The method has to exist somewhere in the inheritance structure. No new arrows for, yeah, oh, right, I didn't mention that. For the game item, for the next constructor, no arrows. If you drew an arrow from game item to weapon, I wouldn't be mad at that at all. But I don't draw them when I'm doing my memory diagrams. If it's there or not, it's not going to affect your grade at all. It's implied here when this, they're both constructor calls and this is a reference to the same constructor. It's implied that you know that that this is another constructor call for the same object. So I don't really need to show, the arrow doesn't show me more understanding on your part. So I don't care if it's there or not. Okay, so we found the move method, we're calling it. This is a reference to the calling object still. And we get dx dy, regular method call from here. Now that we found the method to be called, the rest is just a regular method call. This dot x location plus equals, we're using this shorthand. If you're not used to the shorthand yet, it's this dot x location equals this dot x location plus dx. So we're going to effectively add that to the variable's value. Dx is negative 0.5, so we're subtracting 0.5 from here, and then adding 1.3. Oh, that is a typo. 1.3, 1.3. Oh, no, it's not. I'm just dumb because it's negative. Negative 0.5 goes up to 0.8 because we added 1.3 to it. And then the program ends. Nothing left to do. We hit the closing brace of the main method. That's it. So the big thing, don't forget your super constructor call and which method is called. Start your search in the object type. Always the object type. If you don't find it, go to the superclass and look for it there. Okay. Let's keep a good pace here and move on to the object class. The object class is a very special class in Java. It's built into Java. It already exists in all of your code. And the object class is a class that if you don't explicitly extend any superclass, you implicitly extend the object class. So with game item, we didn't explicitly extend anything. So if we don't explicitly extend anything in our code, Java says, you know what, you extend the object class now. So these two classes are functionally identical. They do the exact same thing. This one just explicitly extends object. This one implicitly extends object. But they both extend object. What this means is that for any object or any class in all of Java, if it extends something, you can go to that class. If that class extends something, go to that class. If that class extends something, you go to that class. And you can follow this chain of inheritance until you get to a class that does not explicitly extend anything or explicitly extends object, and find that that class extends object. Which means every single class in Java extends object either directly or indirectly. So game item extends object directly. Our health potion and weapon classes extend object indirectly. They extend game item, which extends object. So if game item gets all of the state and behavior of the object class, and health potion gets all of the state and behavior of the game item class, well, the state and behavior of the game item class includes the state and behavior of the object class. So health potion is going to get all of the state and behavior of both game item and object classes. So every single class in Java extends the object class, which means anything that is in the object class exists in every single object in Java. Every single object. If you have access to an object, it has the state and behavior of the object class guaranteed. And these contain a few useful methods. There's a bunch of methods in there. The two useful ones for us will be toString and equals. ToString, every single... let me back up. When you call println, the toString method is going to be called. So how do we guarantee that the toString method exists? Well, because it exists in the object class, and every single object in Java extends the object class. Therefore, toString exists in every single object ever in Java. The only place it doesn't exist is with our primitive values. And with our primitive values, there are other ways that Java converts those to strings. So we can call println on any single value in Java, and we will get a string that represents that object. Same with equals. There will always be an equals method. This was in the find method for linked lists. If you recall, the find method called the equals method. And in that method, we were working with generic types. We had some type T, which could have been any Java type at all except the primitives. And we were calling the equals method on that. So how do we know that the equals method exists? Well, because it exists in the object class, and every object, no matter what T is, has to extend the object class, so it has to have an equals method. It has to have toString, has to have equals. It's something we can reliably count on in Java, that every single object will have these methods because they come from the object class, which turns out to be pretty damn handy. We're on to the next one. A little bit ahead of schedule. I like it. So I have, at the start of this slide deck, I have some tips that I had in place for the previous semester. I decided to leave them in. Some of them will be a little outdated, but some of the ones I still want to highlight, I want to go over here and at least talk about these tips. This is when Task 4 was absolutely crushing the class, which, to be honest, might still happen this semester. Task 4 is by no means easy. I gave the warning that there's a big jump up in difficulty from 1, 2, and 3 to Task 4. And then that difficulty should, in my opinion, level off or maybe even dip a little after 4 for the rest of the semester, all the way through 8. Probably level off is probably more accurate. So a few things that were tripping students up last time, which might get a lot of you this time. Don't test undefined behavior. If something's not defined, and this happens every semester, this wasn't unique to Task 4 or anything. Task 4 is just the first one where I'm asking you to do some complex testing. Don't test undefined behavior. If the homework doc doesn't explicitly say what should happen on a specific input, do not test with that input. Just don't test it. If you find yourself in a position where you're guessing what the expected output should be, that's a bad test. You can't have that test because it's testing undefined behavior. And this is different from edge cases. When there are edge cases that have clearly defined behavior based on the write-up in the homework doc, you do want to test those edge cases, but you don't want to test undefined behavior. So it's a subtle difference. But like for Bayesian average, the number of extra ratings, if you didn't read the description yet, which I assume a lot of you haven't, probably most of you haven't, but we're computing the average rating with extra ratings with the value 3, and we're going to add -2 extra ratings. I might have that backwards. or 3 extra ratings with the value -2, maybe. But either way, it would be undefined behavior, because like, what should happen when the rating should be -2? That's an invalid rating. Or what should happen if we add -2 extra ratings? I don't know. I don't know what should happen. And I didn't put in the homework document, if you have this invalid input, this is what you should output. I didn't explicitly put that in the homework doc. So just don't write a test like this. Just don't write this test. Don't do it. The danger with this is if you have a test that's testing undefined behavior and you're guessing what the behavior should be, well, whatever you guess the behavior should be might be different than what my correct solution does in AutoLab. So if I guess something different, because the code has to do something on these inputs, if my correct solution, I guessed a different thing and said an undefined behavior, this is what it'll do, and your test assumes something different, well, you're going to fail the correct solution in AutoLab, because you don't know what should be returned. Once you guess, if you guess wrong, or not wrong, I shouldn't say that, but if you guess something different than what I guessed when I wrote my solution, which is probably just whatever ends up outputting on these invalid undefined inputs, that's going to cause issues with AutoLab. So just a tip, avoid that. And also don't test any methods that are not defined in the homework doc. So you can write extra methods. You can even create extra classes. Any way you want to structure your project to get the job done. So writing helper methods especially can be very helpful. But you can't call those methods in your tests, because again, those methods won't exist in my correct solution. You can only count on the methods that are defined in the homework doc to exist in the code, so you can't test anything that you named. If you chose the name for something, don't call it in your tests. You'll get errors in AutoLab, things will crash. It's just asking for a bad time, and that's going to take you longer to fix your code. Same thing, I don't see this too much in Java, but I used to see this in Scala a lot. Don't test your values of your instance variables directly. They should all be private anyway, so you shouldn't be able to do that. Scala didn't have, Scala was different with its access modifiers, but they should all be private, so you shouldn't be accessing directly anyway. But if you're ever tempted to make them public so you can test them in your tests, don't do that. It's going to cause issues when you submit to AutoLab. All right. Tip number 2, when you create a class, and I talked about this last lecture, so I won't harp on this one, but when you create a class, you need to create an object of that type to be able to test that class, because you need an object of that type to call the non-static methods, or else you can't test those non-static methods. You need an object of the type. You can't test these non-static methods through the class itself, like you did for the problem set, where you said problem set.average. Can't do that anymore. You have to create a new song object and then call the non-static methods through that. And take a look at test classes 1, like we did. I went through it all last lecture. That's your reference of how to test classes. You'll write some comparators. This doesn't really apply because I took away, to kind of nerf this a little bit, I took away the testing requirement of the comparators, so this next bullet point doesn't apply. It was causing, I thought it was going to be a really easy, like a couple minute task, but so many students spent hours and hours on it, doing things that weren't really related to the learning objectives, so I just cut it, because it got way out of hand, more out of hand than I wanted it to be. So you have to rate the comparator classes, but not the testing for them. And try not to get too frustrated. It's going to be a lot. This next bullet point doesn't quite apply anymore. Task 4 used to be most of the work of the next few tasks. It's not quite true anymore, but I think this will still be somewhat true, where task 4 is going to hit you harder than tasks 5 or 6 will. It's definitely not as true as it was last semester, but I think that's still going to be a little true, especially because task 4 is your first really rigorous task that you're doing. So by the time you get to 5 and 6, you'll be battle hardened and you'll be ready for those by the time you get into them. And I think they are a little bit less work, 5 and 6 are. But 4 is going to be tough. So hopefully I've given you enough warning about task 4. Take it seriously. It's not a task to be taken lightly at all. On the plus side of that, this still does apply for sure. If you can survive task 4, you got this. This is what I was trying to say earlier when I say the difficulty plateaus here. I don't think there's a task. There's at least not a task that's another big step up in difficulty. I keep saying this is a step up from 1, 2, 3, task 1, 2, and 3 to task 4. You can think of the difficulty curve. Let me go the right way. As like 1, 2, and 3. I think 1 is a little bit harder than 2 and 3, to be honest. At the end of 3, deleting a node does get tricky, so maybe that one's a little harder than 1. But then 4, there's like a spike up. 4 is definitely up there in difficulty. And then, oops, I didn't move myself. I'm covering up part of the bullet points here. So you're up here for task 4. And then for task 5, 6, 7, 8, I think it plateaus. I think it's pretty much even difficulty after that. So there's not another jump up. There won't be later in the semester where I'm like, oh man, 4, 5, and 6 to task 7. That's a huge, like, I'm not going to be saying that later. There's not another big jump up in difficulty. So if you can get through task 4 and you can keep up that pace for the next 4 tasks, you're getting through CSE116. Assuming you can do the quizzes as well, of course. But yeah, that's all my task 4 pep talk. All right, let's keep going with content. So override. Let's talk about our next big concept for inheritance. Override, I'd say the superclass constructor call. Which methods are called when you call a method? Now you have to look in multiple classes to find what method is being called. And the third big thing is inheritance. So let's talk about it. I'd say those are probably like the 3 things to know about inheritance. Override. Those are like the 3 big things to know about inheritance. Override being the third. I'm trying to think. There's not another big... I think everything else is encapsulated in one of those 3 categories. All right, so what is this? So inheritance, this is review. That makes sense when these lectures are split up across multiple days. We don't really need review right now. So inheritance, we inherit the state and behavior. So here I'm moving the use method to the game item class. I'm going to say every game item should be able to be used. Like, that's what we want to do with these game items. Our player is going to collect these game items and then use them. They're going to use a health potion. They're going to use a weapon. That's our goal. So every game item should have a use method, and we're just going to print item used. Again, we're simulating things, so we're just going to print to the screen, but the item would be used here. Health potion is going to extend game item, so it inherits the use method. So when I use a health potion, it's going to print item used to the screen. But that's not what I want a health potion to do. When I use a health potion, I want the player who used the health potion, I want their HP to increase, which is very different behavior from when a player uses a weapon. So I don't want this inherited behavior. So what I'm going to do is override that behavior, override this method definition with a new definition. So in the weapon class, I'm going to override. I have this, what we call an annotation. So I'm going to annotate my method with the @ and then capital O override. And then create a method with the same exact signature as the method that I'm overriding. So this has to return void, has to be called use with all lowercase letters, and it has to have no parameters. So as long as that method signature, which is the method name, the types and number of parameters, and the return type, as long as those are exactly the same, this is going to override or replace the inherited use method with this definition. Now, if I have an object of type weapon and I'm going through my progressions and I say, okay, the use method was called, I'm going to look in the weapon class and then I find a method of type use or of named use, I'm going to call this method, and my progression stops before ever finding this method. That's going to be the important thing. That's why we went through all the progression things because the progression is going to be different here because we don't use the inherited use method anymore. So the annotation is optional. I like to use the annotation. This is going to tell the compiler, hey, I'm overriding a method. If you don't have the override annotation and you have the same exact signature, then the method is still overridden. The way our progressions work, we're looking in the weapon class for a method named use with the right parameter lists. And if we find it, cool, we found it, and we're going to call it, and we're going to stop our progressions, whether or not the override annotation is there. So it is optional. The big difference is that the compiler won't help us out here. So say we do have a typo here. We have a capital S. We just typed the wrong thing. We held shift at the wrong time. And we have our override annotation. The compiler is going to be like, whoa, 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 whoa. You told me you're overriding something, but there is no method in your superclass called use with a capital S. Fix your stuff. Fix it. Because I ain't compiling this shit. And then you go and fix it and go, oh, whoops, I have a typo here. And then you fix your typo, and then you go on with your day without any bugs. If you don't have the override annotation, the compiler will not catch this because you're not saying, hey, I want to override something. The compiler is going to be like, oh, yeah, you're creating a brand new method called use with a capital S in addition to your use method with a lowercase s. Cool. And you'll have both methods. You won't catch your bug, at least not with the compiler. You'll have to catch it when you run your program and you get just really weird behavior. You'll have to find the bug, find that there is a bug, identify it, and then find the cause of it. Go through your whole debug process. It's just not worth it in my opinion. Just put your override annotation. Let the compiler be a bro and help you out. The override annotation just makes your intentions very clear. Plus, it makes your code more readable. If somebody else, another human, is reading your code instead of the compiler, it just makes it very clear that you're overriding something. Nobody can mistake this and say, wait, are you overriding a method? No, I got my annotation there. You know I'm overriding a method. No question, no confusion. So I like it. Some developers don't. You can form your own opinions, develop your own preferences. I prefer the annotation. Whenever I can be explicit, I like to be explicit. I like that self-commenting code. I'm all about that. I want my code to just shout at you what it's doing through naming conventions, through being explicit about things, etc. Naming conventions mostly is the big thing. And not doing too much in one line. A lot of devs like to show off like how much they can get done in one line of code, which is fun. It's a fun challenge, don't get me wrong. But if you're writing code to be used by other people, like especially in a professional setting, you'd be better off writing self-commenting code. Split that one line into 5 lines or however many it takes to make your make what that line is doing very explicit. All right, anyway, enough of that. Let's get on with some theory. So what happens, this is the big thing, we have 2 use methods being called through 2 different objects of 2 different types, and we want to know which use method is going to be called and how we're going to go through our progressions and how our progressions are going to change now that we have this override method in the weapon class. So first, we hit a constructor. Guess what I'm going to talk about here? Your superclass constructor. I swear, if any of you missed this superclass constructor on the quiz, I'm probably just going to know that you didn't watch lecture. But then you're not hearing me say this right now anyway, so it doesn't matter. I'm not talking to anybody by saying that. Or I know... some of you like to watch lecture at 2 times speed. Hopefully I said this so many times that even at 2 times speed, you're not going to miss that point. But anybody who misses it after I said it so many times, like, I know you just ain't trying. Or maybe you just panicked during the quiz. You know, there's other options, but most likely you're just not trying. Don't forget your superclass constructor call for the love of everything. So your superclass constructor call, weapon extends game item. Game item constructor is called. We have 2 constructor calls to construct 1 single object. Don't forget your superclass constructor call. It's explicit in this case. It's pretty hard to forget when it's explicitly sitting there. When you get to this line of code, you go, oh yeah, that thing Jesse was talking about. Superclass constructor call. Put it on the stack. Same thing with the potion. We're going to create a potion. Guess what? The superclass constructor goes on the stack. So we call the health potion constructor. The health potion constructor calls the superclass constructor, which is game item. So we call the game item constructor. Both constructors go on the stack to create one single object. So new, we only see new twice. So we should have 2 objects on the heap, even though we have 4 constructor calls to be able to get the job done of creating those. So don't forget your superclass constructor, right? And there is a tricky one coming up. I'm not sure if I'll put it on the quiz or not. Probably not. But there is a tricky case that we'll talk about in the next slide deck when we talk about comparators, where the superclass constructor does get trickier, which is why I say it so many times, so you can even get the tricky cases. But I probably won't put that on the quiz this semester. So weapon.use. Here's what we want to talk about in this memory diagram. What method gets called? Now, weapon extends game item, which has a use method definition, but weapon also has a use method definition that has an override, and health potion doesn't have a use method. So which one gets called? Weapon.use. So weapon.use, we're calling the method through an object of type weapon. So we're going to look in the weapon class for a method named use that takes no parameters. And we find it right here, use with no parameters. This is the method that's going to be called. Whether this annotation is here or not, I don't even care that annotation is there or not. When I'm doing my memory diagrams, at least it helps when I'm writing code, and the compiler can help fix my identify my mistakes if I make any. But for the memory diagram, I don't even care that the override annotation's there. I'm going to call this method because I found it in the class matching the type of the object that's being called. I call this method. This is a reference to the object being called, the calling object, always, always, always. And then call the method print to the screen, this dot damage, and we get that print to the screen. So even though weapon extends game item and did inherit this definition that prints out item used never gets printed to the screen when we call weapon.use. Item used never gets printed to the screen. This code never executes. This method was never called. This stack frame never goes on the stack. Nothing happens with this. It's completely non-existent in this method call because we overrode that method with a new definition. So this is the only definition that's used when we call use through an object of type weapon. Only this method, only damage dealt of this dot damage 100 in this case. That's the only code that executes when we call weapon.use. Only one stack frame. Unlike the constructors, we do not implicitly call the super method, the superclasses method. Doesn't happen. Override is a complete replacement of the method. We completely replace this with this. It's really the point of this memory diagram. The next one we actually did see already in the previous, did we? Yeah, we saw this in the previous example, the previous memory diagram. So this is more a refresher. But potion.use, we call this through a method of an object of type health potion. We go to the health potion class. We look for a use method. We don't find one. So we continue our progression to the superclass. We go to the game item class and say, well, maybe we inherited a method named use, and we sure did. So now we do get to see the inherited method, and item used is going to be printed to the screen when we call potion.use, because potion did not override use with its own method, so it still uses the inherited game item method. Yeah, why would you use override if you're going to rewrite the method with a different outcome? So why would we even put this method in game item? So this is what I would call default behavior for anything extending game item. Like health potion extended game item and just said, yeah, I like the default behavior. That use method that just prints item use, that's fine with me. I'm good with that, so I'm just going to use the inherited method. And then if you have a class that extends game item where you want some more custom behavior, you want to do something different, that's when you would override it. But having a definition here just gives a default behavior for any extending class that they're welcome to override or not override. And if you're always going to override it, then there's not much point to having this. And to foreshadow again the polymorphism, if every single class is going to override it and you don't want any default behavior, that's when you would make this method abstract and you would delete the whole body and you would just say everything that inherits me must override a use method is basically what an abstract method means. Everything that extends me needs to override this, but I'm not going to provide a default implementation. So that's what you do if everything wants to override it, which I actually would do in this case. A use method, like health potion, is going to want to increase a player's HP, weapons, like everything's going to have specific behavior. There's no like default behavior I'd want for an item anyway. So this would be a case where I would use an abstract method, but we're not going to have that conversation until we talk about polymorphism. So I'll give you a little bit more than you bargained for with that question, I think. But the short answer is to give default behavior to any class that is okay with that default behavior. And then anything that's not okay with the default behavior, it's going to override. Oh yeah, I forgot I have these two string slides here. I was thinking, man, I was like, man, we're making great time on this slide deck, but I forgot there's a whole nother half to it. Because we do two string and then a memory diagram with two string. All right, so everything extends object. Every object in Java, every object like lowercase o, every object on the heap extends the capital O object, the class in Java. So every object inherits from object, which means they all have toString and equals. They all have these methods, every single thing, including our health potion class. Our health potion has a toString and an equals method. But what do they do? What do these methods do in the object class? The object class defines what toString does and what equals does, but they don't really do what we want them to do in most cases. So if we want some actual meaningful behavior out of these methods, we're going to override them. We can override whatever we inherit from object and replace it with our own toString and our own equals if we want custom behavior. With equals, I actually won't override equals anytime throughout the semester. So I'll just talk about what equals does. The short answer is don't use equals on your objects in your tests. It's not going to do what you want it to do. The default equals that you inherit from the object class will compare the references. It will say, do these two objects refer, or do these two references refer to the same object on the heap? That's what your equals method is going to do. So if you have two song objects in your code and you want to check if those two song objects have the same title, the same ID, the same ratings, the same artist, and you try to use .equals to compare them, or assert equals and give it the two songs, not going to work because the song class inherits the object equals method, which is going to compare the references and say, do these two references refer to the same object on the heap? Even if they have identical values all the way up and down for all their instance variables, it'll return false if they refer to different objects. So don't use equals in your testing. You have to actually call the getters and compare the values that are returned and actually go through that linked list and compare the values of that linked list. You got to do some work on those. ToString we will override. So let's give ToString some custom behavior and override this method right here. So if we look at the object code. The actual object code, there's a lot of code. Again, just like when I had array lists in the math class, I'm removing most of the code there. But this is the relevant part that we want to talk about. In all of these classes, game item implicitly extends object. So game item inherits this method. And then in weapon and health potion, all of these classes have this definition for its toString because none of them override toString. So they all get this method. So if we define a method named toString, capital S, takes no parameters and returns string, then we're going to override this method. And we actually did this earlier in the semester when we introduced classes. We actually did override toString in one instance, but I didn't use the override annotation mostly because I just didn't want that lecture to be more confusing than it had to. I didn't want to add one extra thing on there. But now we're talking about it, so I will have my annotation on the toString methods from here on out. So if we call toString from, say, an object of type health potion, we're going to go through our progressions. Okay, toString in the health potion class, don't find it. Go to the superclass, look for a method named toString, don't find it. Go to the superclass, which is implicitly object, go to the object class, look for a method named toString, and then run this code. This is the actual code for the toString method in the object class, which is going to do this. It's going to get the name of the class, which is the fully qualified name, that's package and the class name, the @ symbol, and then the hex representation of the hash code of that object, which is going to give us some value that's pretty meaningless to us. It means something to Java and the JVM, doesn't really mean anything to us. You can kind of think of this as its reference on the heap, but it's not quite. It's something else entirely. It's not something that we care about. So this, if we just print a health potion to the screen, you're going to see something like this. And if you ever see something that looks similar to this with the @ symbol, random hex value, and the name of a class, fully qualified name, that's an indication that you printed something to the screen that does not have an overridden toString method, and you call the toString method from the object class. Almost always not what we want. Almost, I'll say almost, but there's never been a case where this is what I wanted, unless I just wanted to verify the name of the class, because we do get, like, get class does get the class for the actual object type. So if you want to know if you have a reference to like a weapon or a health potion, it can be somewhat helpful there. But at that point, I would recommend just running the debugger. So really not what you want when you're printing something to the screen or just converting it to a string otherwise. And even the official documentation in the object class says it's recommended that all subclasses override this toString method. So it's basically made, like, you have this, speaking of default behavior, you have this default behavior, but most classes don't want that default behavior, so it's like, hey, you should really override it. We'll give you a default behavior just so you don't have to worry about abstract classes, or abstract methods and abstract classes. We'll give you a default behavior just so we ain't got to have that conversation, but you really should override this. Like, this isn't what you want. So let's override this. And what we can do is override this in our game item class. If we override toString in game item, then weapon and health potion inherit the overridden toString, and they'll both get that toString method. So if we print a weapon to the screen, we look for toString in this class, don't find it, go through our progression. Game item does have a toString, and call this one, and we never make it to the object class in our progression. So we find this this toString and call this one, because this was inherited by weapon and health potion. But we can do better than that even. So maybe our weapon class is... Oh, never mind. So our classes themselves can also override toString. And I'm going to mix my notation here just to emphasize the point that the override annotation is optional. Weapon is going to override toString to print out weapon stuff. And health potion is going to override toString to print out health potion stuff. And there's one new thing here, I mean, besides overriding toString itself, but one brand new thing, brand new concept, is that we can actually call an overridden method. We can call an overridden method using super. So we used super before to call the superclass constructor, but we can also use the keyword super to call a method defined in the superclass. Now, and most of the time we would just call the method anyway. We would just call it without using super dot. But if we've overridden that method, which we're doing right here, we're overriding that toString method. So if we just call toString, we're going to get this method, and we're going to have a recursive method, and we're probably going to go infinite at that point, unless we set up some base case, and we're doing that for some reason. But if we want to call this method, the one that's been overridden, we can do that by taking our superclass, our keyword with our superclass, dot, and then call the method. So this will call this overridden toString method. Now note that this will only go up one level. So we can't get back to my knowledge anyway, maybe there's a fancy way to do it. To my knowledge, there's no way to get back to, from the health potion class, get back to the object toString. But we can go up to the previous toString that was overridden and access that through superdot. So we're overriding the toString method, and this is the situation, this is the common use case for this. We're overriding the toString method, but we don't want to completely replace the old implementation. We just want to add to it. So I just want to add that, hey, this was called from a health potion, which isn't super meaningful just for the example here. But we're going to call the super constructor, or the super, I've said super constructor so many times, my brain just wired to say that. We're going to call the super method, the superclass's implementation of toString, get this string returned, and then concatenate that with whatever we want to add to the method. So very common use case, I want to override a method, but I just want to add functionality to it. I don't want to completely replace it. To do that, I'm going to override the method, but also call the superclass method, and then add to it whatever else I want to do. Very useful. Let's see this in action. So let's go back to the same code. I cut down, as the code gets more complex, I do whatever I can to save space on the slide. So I cut out the main method, the braces and everything. But same start as the last time. We're going to have our superclass constructor calls, 4 constructors to create 2 objects. All that jazz, all that's the same. But now instead of calling the use method, I want to call the toString method and see what happens when these toString methods are called. So in this case, we're going to call println. Now println is internal to Java, so we don't worry about the stack frame created by the println call itself. But we are going to use our knowledge of Java, our intuition and stuff. We're going to say, okay, we're printing weapon to the screen. I'm not tracing through the println method call, but I know it will call this weapons toString method. I think I'll just avoid this in the memory, in the quizzes. We used to put this on quizzes, but I think it's just confusing for no reason. Inevitably, a multitude of students fail because they're like, well, println, you don't have to trace println. I didn't know to call toString. But toString will be called, so you have to know which toString method is going to be called. If I do something like that, I don't think I will this semester, but if I do something like that, just know if there's code that you're given on the quiz, I'm giving you that code because I want you to trace it. So if you get through this, if this were a quiz and you get through the whole quiz and you never have a toString stack frame on your stack, you did something, you missed something, you did something wrong. That's true in general. If there's code that I give you on the quiz and it's never executed, you probably did something wrong. Not always, just in case someone panics if this does come up. Like if there's a conditional, sometimes I want you to know, does the if execute or does the else execute? And I won't necessarily have them both execute in one trace. So things like that. But if you miss a whole method call, you probably did something wrong. Uh, unless it's overridden. Maybe I would have a superclass method that's overridden in both classes and never called. Maybe, but probably not. All right, so what happens when we print weapon to the screen? We're going to get weapon dot toString. So this object is getting its toString method called. So we go through our progression. We're going to go weapon. This object is of type weapon. So we go to the weapon class. We look for a method named toString that returns a string, takes no parameters. We find it. It doesn't have the override annotation, but our method signature matches what we expect for toString. And it has to be exactly this because that's what it is in the object class. And that's what println is going to call and expect. So we find it and our progression ends. This is the method we call. Print out the weapon damage. Oh, I'm just blind. I'm like, why didn't it print to the screen? Yeah, I just didn't see it. Print out the weapon damage. Method ends. Cool. We've pretty much seen that before. It's a little different because it's a toString call, but conceptually it's the same thing. And then potion, we're going to do the same idea. Potion dot toString. So this is an object of type health potion. So we're going to head over to the health potion class and look for a method named toString. We find it right here. We're going to put that on the stack. And we're going to execute this method. And here we have super.toString. So now we're going to go to the super class, which is game item. Super is game item. So we go to the game item class and look for a method named toString. And call this method. One thing I just want to clarify, it's a very small, minute point, but if this override wasn't here, if this toString wasn't here, super would go to the next definition it finds. So it can go up 2 levels. It can go through game item and go to the object class if game item doesn't have the overridden toString. So it can navigate multiple layers, but it'll find the first instance that it finds in that progression, which in this case is in the game item class. So super.toString is going to call this method. I would never put that on a quiz. That's too minute of a point. But just in case somebody's like, oh, I don't know, I think you can do that. I wanted to mention it. So it'll find this method and call this one. So we do have another toString call on the stack. This is still going to be a reference to the calling object. Just like the super constructor, it passes this onto it when you have these super calls. This is going to be the same in the super call as it was in the original call. So this is still a reference to the calling object, the original calling object. And we execute this code, get our location, return it. I'm not storing it in a variable, so I don't have to have a return arrow here, because I don't know where I would point it to. Probably just the stack frame. If you were to draw a return arrow, I would draw it right to the other stack frame. But this resolved to x colon this dot x location, y colon this dot y location. And then we're going to concatenate dash health potion to that. That's what we're going to return, and that's what's going to eventually be printed to the screen. And we'll see this printed to the screen. So super.toString got this implementation, and then we concatenated dash health potion to the end. Whew. As always, if you ever have questions, let me know. I'll look for questions, but I'm not going to wait for the latency because I'll be sitting here for at least half a minute doing nothing. I'm too impatient for that. So I'm going to move right on to the next one, which we're... Yeah, we're actually ahead of schedule, which is good because this is 57 slides, which is the rough estimate for timing is 1 slide per minute. For this class, it's slower than that. So we did 39 and 34 and took almost the first hour and 40 minutes. It took an hour and a half to get through those. And this is 57, so I wanted to make sure I got to this one quick enough that we have enough time to get through presumably an hour plus of content. Some of the slides do go pretty quick in this. There are some slides that I don't have a whole lot to talk about. So I'm confident we'll get there, but I do want to get it started. And I'm glad we got it started with a little bit of time, a little bit of extra time. It's a, by the way, if you're making presentations for like a class and it wants your professor wants like a 10-minute presentation, it's a pretty good general rule of thumb: 1 minute per slide. You should be making 10 slides for that. You can. It's common to think that you're going to get through slides a lot faster than you actually will. You prepare 20 slides for a 10-minute presentation and you only get halfway through. If you're explaining a slide, even if you're doing the robotic, like just reading your slide during your presentation, it takes roughly a minute if you have decent content on each slide. All right, inheritance and comparators. I left this side note in. Oh, excuse me. Oh, I had a typo on one of the slide decks. I forgot to point out, but I had a typo somewhere. It said, I think, Hame item instead of game item in one case. For anyone who caught that, I should just update when I find these things. Here's another instance of that. I think we do this somewhere in the repo, but I forget where or why. Oh, maybe it was just compare linked lists. Because I think compare linked lists is somewhere in the repo, but I don't think this is relevant for any of your homework assignments. Will you fail if you forget to add the space after Y? No. All right, I was gonna mess with you and joke around, but no, I don't even want to mess with you. No way. Nope. That would be absolutely minor. Has nothing to do. Like for the inheritance quiz, I want to know, do you have that superclass constructor call? Do you know what method is going to be called when there is a method call? Like, do you know how to go through your progressions and find which class, which definition of that method from which class is actually going to be used? And to going along with that, what overrides occur? How do overrides affect your progressions? Those are the big things that I'm going to test you on in that quiz. Those are the learning outcomes that I want you to get out of this content. That's what I'm going to be assessing on the inheritance quiz. And nowhere in there is there any room for, oh, you forgot the space, you fail. There's just no room for that nonsense. I know that happens in some other courses, and I've taken, back in my day, I've taken computer science courses where that was the case, where they were looking for the littlest little things, and it always pissed me off. Now, there's specific learning outcomes, and making sure that you get your space before the Y is not a learning outcome of the course. I want to just say you're joking and joke back with you, but I know there are some courses and some professors who do care about that space. I had not to get too lost in the woods here, but the first programming course I took, it was a C++ course. For what it's worth, it was just intro to programming for engineers. I was going for engineering at the time, and then dropped out and came back to as computer science. But that's a whole nother story. And for the exams, it would say, write a program that does XYZ, whatever. And we had to write code on the exam paper. We had to write the program. And if there were any syntax errors, he would go through and he would be the compiler while he was grading. And any syntax errors would be all marked up in red and -5, -3, we would lose points for every single little thing, including spaces in our print lines like that, or in our couts in that case, including the things like package declarations, import statements. If we forgot an import statement, that's points off. If we forgot a semicolon, that's points off. If we didn't remember the syntax for using namespace std semicolon, which now I remember because it was hammered into my freaking brain because of this. If we didn't do that, points off. If we didn't have our return type of int on our main method, that's points up. Every single little thing was points off. And I feel like most of that had nothing to do with the learning outcomes of the course. Like, it didn't affect my ability to write a program because, you know, the tools that I use when I sit down to write code are going to fix all that stuff for me. Granted, the tools weren't as good back then either. We were mostly just using text editors, but they were actually, no, it was Visual Studio, wasn't it? Visual Studio caught all that stuff for us. So it was just frustrating. And even if it didn't, we would have a reference. I would just Google it like I do these days. When I forget some syntax, I would Google it. What's the syntax for this? How do I remove something from an array list? And it'll tell me, and I'll do it. Like, it didn't have anything to do with what we would actually be doing. So now that I'm on the other side of things, I don't like doing those bullshit things where, oh, you missed your space before your Y, you failed the quiz. You need to understand that space will be there. Or sometimes even worse, if the difference between print and print line, if I do print and then print line and you put those things on two separate lines instead of on the same line, oh, that you failed the quiz. Like, no, we don't do that stuff. We don't do that around here. If any of my colleagues do that, snitch on them to me. I want to know so I can go yell at them. That's crazy stuff. All right, I could talk about that all day, but we got to move on. Which at least one outcome of that is I did learn my syntax to a ridiculous degree, so I could pass, so I could ace those exams. But it was dumb. I could have used that brain power for something else, like actually solving problems. So all right. So this side note, I don't think we do this anymore, but I think it's in the repo. If you zone out for this slide, I wouldn't mind so much. But you can use generic types on methods. Even if you are in a class that doesn't use generic types, you can have methods that use generic types, and that's the syntax for it. You put your generic type right there in between the access modifier and the return type, and you can use that generic type all throughout. And this method can be called on a linked list node of any type if you have two linked list nodes that you want to compare. But this only works if the values for that linked list, if t is something with a meaningful equals method, which isn't true for our song anyway, and that's the one linked list that you're going to be comparing: songs, movies, ratables. But if you do run into this in the repo, just know that that's legal. It's allowed. It's a method that takes a type parameter or a generic type. Moving on to the good stuff. Okay, now I need you to pay attention. The last part of homework 4 is going to talk about comparators. There's a comparator class that you have to create. For the comparator class, just grab it from the repo. It can be identical to what we have in the slides here and in the repo. And then it asks you to extend that comparator class into concrete comparators, and you do have to implement those comparators. And spoilers, both of those should be one line of code. If you're writing more than a line of code, or maybe the way you do it might take 2 or 3. If you're writing more code than that, you're overcomplicating it. The comparators are supposed to be a pretty quick add-on to this. Just another example of inheritance. You're not meant to get lost in the code of those two. It was just getting you used to the extends syntax, the override syntax, and all that stuff. So don't get too lost on the comparators. And a lot of students get lost on those when it was meant to just be a quick tack-on to the assignment. Granted, I had them testing their comparators too, and testing them is actually pretty hard. So to be fair, it was a little trickier than it needed to be too. But comparator, we want to compare two values, and we want to use the comparators for sorting. So if we're given two values, we want to know which one comes before the other in sorted order, so we can use these comparators for sorting. There's 2 flavors of comparators. This slide I can probably get rid of soon, but since you had JavaScript in 1.15 still, just the timing of the course, we're dropping JavaScript from it, so this won't be too relevant. Actually, this will be. Actually, Java does this as well, but all right. But anyway, comparators come in 2 primary flavors. There are other styles and stuff, but these are the 2 primary ones, or variations of these 2 that you'll see out there. 1 returns an int. It's going to return a negative int if the first input comes before the second, and positive if the second one comes before the first, and 0 if they are tied in order. This is the way it worked in JavaScript. When you use that, you have your comparator that returns an int, and these usually return either -1, +1, or 0, but not always. So whenever you're using one of these comparators, you should say less than 0, greater than 0, 0 in your conditionals. If it returns less than 0, I know the first comes before the second, etc. The other flavor, the one that we're going to use in this course, the ones that you'll write, are returning a Boolean. It's going to return true if the first input comes before the second input, and false otherwise, including ties. All right, so the first style, int, and this is what Java's compare to method will return. And compare to is going to be a little, actually compare to isn't going to be super useful in your homework, but the string class, and I believe I put this hint right in the homework doc. I don't think I'm spoiling anything here. But the string class has a compare to ignoring case method, which will compare two strings, and as the name implies, ignore the case. It also has equals ignore case. So those methods might be super handy in your movie class, where you need to check if two array lists contain the same strings where the case can be different. Compare them, making sure that they're the same ignoring case is going to give you exactly what you want for the homework. So you don't have to worry too much about how do you actually compare two things where the case doesn't matter. Just call the built-in Java methods, or you can call two lowercase on both of them and then compare if they're equal. But handy methods that you have. But the Java built-in compare methods will be of the first style, where it's a negative int if the first object comes before the second, and the first one is going to be the calling object in the reference this, and negative or positive the other way around, and then 0 if it's tied. So if I have the strings 1 and 2, if I do 1 compare to 2, the first argument is going to be 1, which is stored in the reference this, and the second one is the argument, which will end up being the parameter. And this is going to return -1 because the calling object comes before the parameter. If it's 1 compared to 1, they have the same relative ordering, so it returns 0. And if we reverse the values, 2 dot compared to 1, we're going to get 1, because 2 should come after the 1. And this one will, -1 and 1, will return those. Not always the case, not true in general. Any negative integer is valid here, any positive integer is valid here. Strings are compared alphabetically. And there are some special differences like this when we want to sort strings. This is the default sorting order for Java. Java's going to go through the characters of the string, and if one of the characters comes before the other one, then the order is determined. If the characters are the same, move on to the next character. If the end of one string is reached, that string comes first. So if one string is a prefix of another one, the prefix string is going to come before the longer string. So the end of a string counts as coming before any other character. And if case matters, if you're just using compare to and not ignoring case, all lowercase letters come after all capital letters. So capital Z, for example, comes before lowercase a. The entire capital alphabet comes first, and then the entire lowercase alphabet. So this can really throw off your ordering if you're taking case into consideration, which is always a really weird bug or feature, however you want to look at it. If you have if you have files that are named, some starting with capital and some without, and then you sort them and they're in a default sorted order, and all the capital ones are coming before all the lowercase ones, it's just awkward. So usually we want to ignore case when we're sorting strings, which is true in the homework. We're going to sort and compare ignoring case, which is why that's in the homework. It's a very common use case for sorting strings. We usually want them sorted alphabetically while ignoring case. And we don't want the case to change our sorted order. It's just awkward. All right. But as I mentioned, the Boolean flavor, this is what we're going to code in class. This takes two parameters, so we're not taking advantage of this dot at all. We're going to take two parameters and return true if the first one comes first and false otherwise, including ties. We'll see this at some point. Will we see this? It might have been in the bonus, not bonus content, but the advanced content that I had to cut for the summer. But we can use this to get the full order. For example, if it returns false, how do we know if the second parameter comes before the first one or if it was actually a tie? So we can actually identify a tie. Oh, this will come up when we do trees, actually, in the next lecture. So we can call the comparator one time with, say I want to compare x and y. I'm going to call this comparator, I'm going to say compare x and y. And if it returns false, I can then call it again and say, hey, compare y and x. I'm going to reverse the order of the arguments, which reverses the parameters. And then if it returns false again, I know x and y have the same value. Because if x doesn't come before y and y doesn't come before x, then I know that I have a tie on my hands. So we do get the full information of the other style of comparator, but we might have to do a little bit extra work on our calls to get that information if we're concerned about ties. We're going to see that in binary search trees to determine if two values are equal, we're going to call the comparator twice with the parameters in the reverse order. All right, so let's write ourselves a comparator. For this, we want a compare method, which is going to compare two values. So for this case, we're going to take two ints, and we want to sort ints if our fully sorted order is decreasing order for integers. We're going to use the greater than symbol. So the default ordering for integers is going to be the less than operator. We're going to use the less than, and that's going to sort in increasing order. But just to switch things up a little, we're going to sort in decreasing order. So we want this to return true if A is greater than B and false otherwise. So we're going to return A greater than B. So if A is greater than B, this will be true, and we're going to return true. If they're the same, or if B is greater than A, this is going to return false. So we meet our criteria for a comparator. We're returning true if A comes before B. A should come before B if A is strictly greater than B. That gives us our decreasing order. And false otherwise, including ties. So we don't want to put greater than equal here because our tie should be part of the false return. So this is our compare method. But we're in the middle of inheritance, so let's slap some inheritance on here. Classes and inheritance. We didn't even get classes yet. So let's wrap this up in a class so we can call this method. And we're not going to make this method static, so we will actually need an instance of this class to be able to call our method. And we don't have any constructor here. This is where the superclass constructor, eventually we'll get to that part. This is where the superclass constructor, when we get to it, is going to be a little bit trickier. So how are we going to create an instance of an object, which we need to do because this is a non-static method? How are we going to create that when we have no constructor? Well, no worries. If we don't put a constructor in our class, we actually get what's called the default constructor. The default constructor takes no parameters and does nothing. So if we don't have a constructor explicitly, we implicitly get the default constructor, which means these two class definitions are functionally identical. This class implicitly has a default constructor with no parameters and does nothing. So if you don't have anything to initialize, you just don't write a constructor, but you can still call that constructor, but I can only create an instance of int decreasing if I call the constructor with no parameters. So that's the only one that exists. And let's slap some inheritance on here because it's the inheritance lecture after all. So we're going to write a comparator class that's going to be able to compare any type. So we're going to specify a type parameter or a generic type in Java. Oops. Let me get out of the way here. We're going to specify a generic type and then have the compare method take two values of that type. So we're going to have a comparator of a type that can compare two values of that type. This way we can compare any type, two values of any type that we want. And then in our int decreasing class, we're going to switch this up a little bit. We're going to say extends comparator, and we can actually specify the type in this line as we're extending. So we're not just going to extend comparator or comparator of t. We're going to say, for this case, I want to create a comparator of integers. So int decreasing is only intended to compare integers. So we're going to extend comparator of integer, which effectively turns these t's into integer. And then when we override compare, since t is integer in this case, compare is going to take two objects of type integer. And then we have our implementation that's the same as it was. We have to use integer instead of int because we're using it as a generic type. Generic types can only be class types, not primitive types. So we do have to switch this to integer. It's the only time I'll ever use the auto box, the boxed types, this capital I integer. Only time I'll ever use it is when I have to. In this case, we have to, so I'm going to use capital I integer. There were still Piazza questions about that. I feel like I harped on that so much in lecture. I still had students with capital D double as the return value of the, I think, the average method. I think that's where it always shows up. And every semester, like I don't know how many more times I can say it. The feedback in Autolab even says, hey, you got a capital D double here, what the fuck? Anyway, I have to change it to integer here. Any other case, I'm going to use int as long as I can until I have to use integer. But here we have to use integer. So the compare method, since we don't want to talk about abstract methods, I know I mentioned them a few times, we don't want to go fully down that road right now. We're going to give some default behavior here, but this default behavior is intended to be overridden by every class that extends it. So here's an example of a case where this should always be overridden, because always returning false isn't that useful for a comparator. We never want that implementation. And we'll revisit this when we talk about polymorphism and change this into, actually we'll change this whole thing into an interface, as it should be. And this is a full class. When we extend comparator, we have a full class here. We can do all of our class stuff. We can have instance variables. We can have helper methods. We just have to have the compare method because it's part of extending comparator. But we can also have anything else that we want. So if I want to compare game items from their distance to the origin, I can do that. I can write a helper method, call that method twice, use the less than to sort in increasing order. I can do that. If I want to sort game items from their distance to a reference game item or their distance to a player, maybe, I can have a constructor that takes a reference to a player, stores that in an instance variable, and the distance method will find the distance between the item and that player, and then sort the items according to the distance of the player. We can go crazy with these things. We can do a lot of stuff with these comparators, but for lecture, we're going to stick with this int decreasing. We're going to keep it much simpler because I want to focus on what comparators do and how they work without getting too lost in the details of really complex comparators. But my next question, we want to sort, since we're sticking with ints, we want to sort integers, and we're going to sort array lists. So say I have an array list of integers. I want to sort these things, but the only tool that I'm given to be able to sort them is a compare method that takes two values and compares two integers. So how am I going to sort a data structure with any number of ints when I can only compare two ints? How are we going to do that? And the short answer is we're going to call the compare method a bunch of times. But let's throw an algorithm at this and get an example of how we can do that. And we're going to do insertion sort, which you probably saw in 115. So I'm not going to get too bogged down on the details of insertion sort, but we will go over it and review it, especially if you haven't seen it before. I think in 115 they usually do either insertion sort or selection sort. Or maybe they do both still. I don't remember. But whether it's review or not, the idea here isn't hard to grasp for a 116 student. You already made it through 115. So I think this will be pretty good. But anyway, let's just go over it. So for insertion sort, we're going to go through each value in the input list. And we're going to copy each value to the output list in the location where it belongs. So I'm going to start with the first value here, 1. And I'm going to copy that to the output list where it goes in sorted order. So with 1, there's no decision to make. The output list is empty. There's only one place to put this value, so we're just going to add it to the output list. Done. Then we're going to advance to 6. When we get to 6, we have some decision to make. We're going to take 6 and go to our output list and figure out where it belongs. To do that, we're going to use our comparator. So we're going to compare. We're going to say, does 1 go before 6? And we're going to go down the output list asking that question with every value until the comparator says no. Once the comparator says no, that means we found the location where to insert that value. And remember, we're sorting in reverse order. So we're going to say, does 1 come before 6? The comparator says no. So when this list is just the value 1 and we say, does 1 come before 6? The comparator says no. Well, that means 6 is going to be the new first element in this list. So we're going to insert 6 at index 0 and shove 1 down the list by 1. And we're going to do the same thing with 5. We're going to find out where 5 goes in this list. So let me set on this slide. We're going to find out where 5 goes in this list. To do that, we're going to say, hey, comparator. So we're calling our comparator multiple times here. We're going to say, hey, comparator, does 6 come before 5? Comparator's going to be like, yep. So we're going to move on because that means we haven't found the place where 5 goes yet. Hey, comparator, does 1 come before 5? Comparator's like, no way. 1 doesn't come before 5. 1 comes either after 5 or tied. If this were a tie, the comparator would still say false. Either way, we found where 5 belongs. It goes right in between 6 and 1 because the comparator returned true until we got to 1. So this is where 5 goes. We're actually going to insert 5 at index 1 and shove 1 down the array list by 1 position. So for each value, we're figuring out where it goes in the output list and then inserting at that location. And there's the code. I like hitting you with code all at once. But we're going to look at this code for a bit, even though it all appears at once. So let's look through this. This is the code that does exactly what we just visualized on the previous slide. So let's pick this apart and see what's going on here. And the first part here, like before we get into the actual sorting algorithm, I want to talk about the setup here because there's a lot going on here that's combining some things that we've seen already in a way that makes this extremely versatile. So our sorter class, which is going to implement insertion sort, is taking a type parameter t, which means when we create a sorter, it can sort any type. It's going to take a type and sort that type. This code also takes a comparator of that type in its constructor, stores that comparator in an instance variable, and then we'll use that comparator. Oh, I forgot my this dot. I always like being explicit with my this dots. I missed one right here. And then calling the comparator when we need to compare values. So the sorter class takes a type parameter and also a comparator. What that allows is it allows us to write a sorting algorithm that can sort any type in any way. So we take a type and we take a comparator. This sorting method doesn't know what it's sorting and it doesn't know how it's sorting it. It just gets an array list of some type. It'll return an array list of that type, but sorted. And it'll use this comparator, call its compare method, to figure out how to order these values. So this is completely generic sorting. We write this sorting method once, one single time, and then it can be used to sort anything in any way. Very, very powerful stuff. And if you think about it, you've sorted, like when you do custom sorting in 115, you'll sort Python lists by some key. You'll sort JavaScript arrays using some comparator. When you call that sorting method, the developers of those languages, and including Java, the developers of Java in any language, they'll write one sorting method, or at least one what we call comparison sort method using a comparator like this. They'll write one sorting method one time, but they'll have it built so generically like this that it can sort types that they couldn't even dream up when they were writing the sorting code. Some health potion class that we made, like that sorting algorithm can still sort health potions by their increase variable, for example. And they don't have to rewrite, we don't have to rewrite a sorting method. We just call the sorting method that exists, give it the tools that it needs, mainly a comparator, and then it can sort our stuff just fine. So we're writing code that can be reused in so many situations that we don't even know what those situations might be, but we can write code that can handle those situations by taking a generic type and a comparator that can compare values of that type. Whatever that type may be. Could be any type, except our primitives. Can be any type, even types that don't exist yet. Very generic, very powerful idea here. Okay, now let's get to the sorting code itself. So we're going to get an array list of type T. We don't know what T is. We don't care what T is. It's some type that matches the type of this comparator. That's all we know, and that's all we care about. We're going to create a new output array, and we're going to end up returning the output array. Now, this input is a list, an array list that we get by reference. We've talked about this, but now that it's had time to settle in, I want to reemphasize this point. We get a reference to an array list, and whenever we get past a reference in one of our methods, we need to be careful about what we do with that reference. We need to be at least mindful of the effects we can have on the overall program. Any change we make to this array list is going to affect the heap, and that change is going to persist even after our method call is done. So we have to be careful about this. Maybe we want that. Maybe we want a sorting method that actually sorts the input and does that inline and returns void. Maybe we want that. Or maybe we want to leave that intact and return a new array list with the same values but in sorted order. And either way is fine, but you need to be mindful of what one you choose and if that's what the people calling your method are expecting it to do. Because they're very different implementations. And I mean that like in general throughout your career. In 116, the homework doc's going to say which way to do it. But when you have a reference and the homework doc says, take a reference, then return something, your Bayesian average method is a good example of this. You'll be called Bayesian average. You'll have a reference through this. It'll be this dot. But you don't want to actually change anything with anything on the heap. You just want to compute what the Bayesian average is and return it. You don't want to make any changes to the heap. A common mistake is to actually add the fake ratings to the list, to the ratings list, and that's a no-go. That doesn't work. So we're going to create a new output, new array list, and leave this input completely intact. Something you always need to be mindful of when you're handling references as parameters. Be careful what you do with those references, because the caller of this method might not want side effects. And then we're going to iterate over the values of the array list. I don't think I've shown one of these loops in lecture yet, but it shouldn't be too complex to understand. It's when we were doing maps, we iterated over either the keys or the values, and we use that through what Java calls an enhanced for loop. I call it a for each loop because that's what it's called in other languages, and that just stuck with me. A for each loop. We haven't seen one of those with array lists yet, but we can use the same syntax with array lists. We have the type of the values in the array list, a variable name that we choose, and then colon, and then the array list itself. This will iterate over all the values in the array list, and then we don't have to mess with for int I equals 0, I less than input.size, I plus plus. We don't have to mess with all that. We can use this syntax. It's a bit cleaner, and it's less error prone. We might mess up our indices if we're iterating over the indices and then grabbing the values. But if we iterate over the values directly with this for each loop, it's a lot cleaner way to iterate if you want to iterate over every value of an array list. And we're going to keep track of the location. This is where we're going to eventually insert the value. Location starts at 0, and then we're going to iterate over everything in our output list. And if our comparator says the value from the output list comes before the value that we're inserting, then we're going to increment location, effectively move down the list one time in that location where we're going to insert. And then we're eventually going to add that. The add method for an array list can optionally take a location, which is the index where we want to insert. It's going to insert this value at this index, and anything at or after that index will get shoved down the array list by one position. It's not going to work for linked list nodes because we didn't write an iterator for our linked list node class. And I didn't provide an iterator on purpose because I want you to check for null and stuff. If you could do this with a linked list, you wouldn't be learning much about linked lists. You're getting practice with recursion. You're getting practice with null checks. You're getting practice with just how linked lists behave. If you could use this syntax, you'd be learning a lot less. It'd be a lot pointless. And honestly, I'd have to make the homeworks harder if you could use this, because I'd have to test you on some other way to make sure you understand how linked lists work. Bummer. I mean, I can make it harder if you want. I know there's lag, so you didn't hear me say that yet when you typed it, but I need you to understand how linked lists work one way or another. If you could use that loop, I would just have to assess your understanding some other way. Instead of having you remove a node, I'd have to do something more complex. So either way, you have to understand how linked lists work. You shouldn't even be looking for shortcuts like that. You need to understand how linked lists work and how to work with them in your code. If you find some shortcut, or some of my assignments do have cheese from time to time. Like if you find the cheese and cop out, it might sound cliche at this point, but you're only cheating yourself. Like you have less understanding, and then God forbid you go to a job interview and they're like, "So how do linked lists work?" And you're like, "I don't know, man. I cheesed it. I just used some cheap ass way of getting around the assignment." And then, yeah, thanks. We'll let you know. You're not gonna call back. You got to understand this stuff. I don't want to go too far down this, but it's just one of my pet peeves when students are constantly trying to find the easiest way through the current assignment instead of trying to understand how things work and then just actually getting their education. I'm not saying that's what you're doing, by the way, either. But I just have years and years of built up students trying to do that, so I'm always on edge about anything that even remotely smells like something like that. I'm like, oh no, not again. So anyway, we're getting off track. And then insert at that location. All right, I finished that slide. And then everything, there's no static anything in here. So we need an object of type sorter if we're going to call sort. And we need an object of type comparator if we want to pass it a comparator. So that's new. We need a new object of type comparator. And we need a new object of type sorter so we can actually call the sort method. But wait, I'm trying to pull a fast one on this slide. New int decreasing is an object of type int decreasing. The sorter constructor takes a parameter of type comparator. Now, this is a sorter of type integer, so it needs a comparator of type integer. And int decreasing does extend comparator of integer. So the T part is right, but can I do this? This is of type int decreasing, and this is of type comparator of t. And actually, we can. Yep, we can do that. We can just do that. We can do that. That's mostly all I want to say about this. It is polymorphism is the reason we can do that. The short answer is that because int decreasing extends comparator of integer, since I'm giving it an object of a type that extends the type that I'm expecting, it's actually allowed. It's polymorphism. We'll have a ton more discussion about this in a week and a half. For now, I'm just going to leave it as this is allowed. We can actually do that. And it's a really cool concept that we'll talk about in depth later in the semester. Really powerful polymorphism is. But not for today. Today is all about just inheritance. We used to teach inheritance and then polymorphism back to back. And students always got confused. No one had any idea what inheritance versus polymorphism was. They just saw it as one big concept because they were taught back to back. So we make an active effort to separate them these days. But that's one crossover that's kind of hard to avoid unless we just don't talk about comparators at this point in the semester. We could push all the comparator stuff to polymorphism week. But anyway, so let's do this. So we need to call the sorter constructor. But before we do that, we need to resolve all the parameters. This is something we don't talk about too much these days. We usually don't nest calls like this. But whatever's inside the parentheses, just like in math, has to be resolved first. So the first thing this code does is going to resolve this int decreasing constructor. So we're going to get the int decreasing constructor on the stack. Now, remember, there's no explicit constructor. So we get the implicit default constructor of no parameters and does nothing. And here's the... There's no way I'll put this on the quiz. I can't put this on the inheritance quiz. But this is where the default constructor or the superclass constructor call gets really trippy and really easy to miss, to be honest. Is we have a constructor call that isn't in the code. So we know we get the default constructor, but that constructor does still go on the stack. And since we extend comparator of integer, the superclass constructor is also still on the stack. So that default constructor still implicitly calls the superclass constructor that also is the default constructor that takes no parameters and has no definition. But that superclass constructor does still go on the stack. We still get it on the stack. So int decreasing, this new int decreasing does put 2 stack frames on the stack, 2 constructor calls. We still get the object being created. Even though this object doesn't have any instance variables, we still put it on the heap. It still exists. It's only there to call this compare method. But all of this stuff does still happen. It needs to be on the stack. Shit, there's one other thing I was going to say there, and I lost it. Hope it wasn't too important. So don't forget your superclass constructor call. I don't think I'm going to get... I'll just stick to it. I'm not going to get this tricky on the quiz. I'll have explicit constructors and constructor calls that take parameters and instance variables and all that stuff. Because there's a lot of like invisible stuff that happens here that you just have to know does happen still. Oh, that's what I was going to say. And technically, the object class constructor does also get called. It does also go on the stack in reality. But again, since it's internal to Java and we don't have access to the code right here, and I'm not going to give you, like I could just give you the object code on the quiz and have you trace it, but I'm not going to. But that does actually in reality go on the stack with its own stack frame. For our memory diagrams, we're not going to bother. We're not going to put the object constructor here, but whenever an object is constructed, there would always be an object constructor stack frame also. We just don't worry about it in our memory diagrams. And for new int decreasing, this has been consistent throughout. Been consistent with this, but just to mention explicitly, because the slides reminded me to say it, is that the return value of this doesn't get stored in any variable on the stack or the heap. It doesn't get stored in any variable, so I don't need a return arrow here. You could draw the return arrow. I don't even know where I put it in this case. Maybe around like this. I don't know. But you just don't need a return arrow if the return value is not being stored in a variable. For sorter, for this constructor call, the return value is being stored in a variable. So we're going to draw a return arrow for this one. And its parameter was finally resolved. It's this OX350. So comparator, where are we? Comparator, the parameter gets the value OX350 because that's what new int decreasing resolved to after these two constructor calls. This is going to be a reference to the object being created. And then the constructor assigns this dot comparator to the parameter comparator. Hey, we're looking pretty good on time. So then list is going to be a new array list. We're going to use our kind of shortcut syntax. Arrays.asList is going to give me these three values in a list, which can be thrown in the constructor of an array list. Array list has multiple constructors, so we'll call the one that takes a parameter and use this arrays.asList to match the parameter type, which is list. If you want to know how that's working or why we do it like that. Remember, our array lists on the heap are going to use this kind of T diagram, indices, and then values at each indice. We had 1, 6, 5. So at index 0, we have 1. At index 1, we have 6. At index 2, we have 5. And I'm picking a random, whatever number pops into my head. When I made the slide, it was 6, 4, 5 was that number. So that's what I put there. Probably because there's a 6 and a 5 here, and then I just pulled 4 out of somewhere. So we got our array. And then we're going to have some variable output that we put on the stack with no value. Our return arrow is going to point there because sort is going to return a new array list and store it in the variable output. Sorter.sort. We only can call the sort method through an object of type sorter because this is not a static method. So we take our sorter object .sort and then pass it the list that we want to sort. So this sorter dot sort, we're calling sort from this object of type sorter. So we go to the sorter class, look for sort method, we find it. Input is going to be list, copy that reference in there. Input stores a reference to this array list. Create an empty array list. I was feeling 987. So 987, 6, 5, 4, 3, 2, 1. Oh, that's what I did. Cute. All right. I forgot I did that. But so we have this empty array list that we're going to initialize. Then we get to our loops. All right. So we have a nested loop too. So we're going to get some fun loop action here. So we're going to initialize before that. We're going to create a variable value to insert, which is inside the loop. So we have our dashed box for our code block. Value to insert with the value, iterating over the values of input. So the first value of input is 1. So it gets the value 1 because that's the first element in this array list that it's iterating over. Location initialized to 0. And then for the next loop, we're iterating over, we have value to compare, iterating over output. Output is this array list, which is empty. So this loop is not executed at all. So we're iterating over all the values in this array list, which is an empty array list. Loop doesn't do a damn thing, doesn't do anything. Then we hit our add. We're going to add at the location 0. So at index 0, we're inserting value to insert 1. So at index 0, we get the value 1 in our output. We roll it again. All right, so we're advancing to the next element of input. We just did 1, so we're going to cross out 1, go to the next element, which is 6. We get 6 here. We're going to reinitialize location We are actually creating a new variable. We have a new variable declaration. Whenever you have the type and then a variable name, you are creating a new variable. So technically, this location was removed from memory. A new variable called location was added into memory with and initialized to the value 0. Paul and I kind of went back. Paul, one of the other instructors, we went back and forth a while on how to do the syntax of this. We're going to have another dashed box for each iteration of the loop to store each copy of each of the variables. We finally landed on, let's just pretend that the variable's reinitialized, at least the way we annotate it in our memory diagrams, mostly because it saves space. Things get really messy if you have an extra code block for every iteration of the loop. So we're going to cross it out, pretend it was reinitialized to 0, and it might seem silly crossing out 0 just to write 0. That would be, if you didn't do that, that would be a minor mistake on the quiz and wouldn't affect your grade if that was your only error. But we're going to cross out the 0 and write in 0 to show that, no, this variable was redeclared as having 0, even though it looks like a reassignment here. So a little caveat, and another one of the little shortcuts we're going to use with our memory diagrams to keep them a little bit tame, a little bit tamer. All right, and then we hit our loop, and now this loop is going to do something. So we have an inner loop, we have a loop inside a loop. Unlike stack frames, code blocks do nest. We can nest these in each other. I'm covering up a little bit here. I didn't move myself for this memory diagram, but I'm not covering up anything important. Just the types: array list of integer, and then system.out.println. I think you can assume what's behind my head there. So code blocks do get nested. If we have a code block inside a code block, we do put a dashed box inside a dashed box. Unlike stack frames, which we're about to see, stack frames will always go below, will always be added to the top of the stack. Below visually, the bottom visually, but the top conceptually, the way we think of a stack data structure. So we put this value to compare inside its own code block inside the other code block. And then we iterate over output. The values, which is 1 is the first value. And then we're going to call this dot comparator. So this dot comparator dot compare. We called compare through an object of type int decreasing. So we go to int decreasing, find its compare method, and this is the method that we're going to call. We gave it value to compare, which is 1. So A got the value 1, and then B is going to be value to insert. Value to insert is the value 6. So we have this stack frame, which went below the other stack frame. Stack frames are never nested. You cannot cross these solid lines. Stack frames do not go inside each other in memory like in reality. We don't do them like that. But code blocks do actually nest like this in reality. So that's how we represent them in our memory diagrams. It's not something we just made up to be annoying. That's actually how things do work in the computer. All right, and then we're going to compare. Is A greater than B? False. Stack frames don't go inside stack frames. So that's false. So we're going to return false, which means we skip this location plus plus. This stack frame ends, so we cross it out. Again, I gray them out in my slides, but in your memory diagrams, you would cross them out. And then that's the end of this loop. We've reached the end of the output data structure. That would be before the insert. And then we add at location 0, so at index 0, the value to insert, which is 6. So at index 0, we put the value 6. And anything that was at or after that location gets shoved down the list by 1. So 1 moves down to index 1. And we do it again. So we were at 6. Now we're advancing to 5. So our value to insert, we're moving through this data structure, this input data structure. Location, reinitialized, or redeclared rather, to 0 again. And we're going to go through this loop again. So value to compare in output, now it's 6 and then 1. So value to compare, a new loop. Even though it's the same code, we do hit the loop again, so we create a new code block here. The other code block is out of memory. This has been deleted. You would cross it out. Value to compare is 6. Call our comparator with value to compare, value to insert. Is 6 greater than 5? This time we get true. Location is going to increment to 1. And then we go back to the beginning of the loop. We're at 6, now we're at 1. Call compare again with 1 and 5. It's going to return false, so we don't increment the location. So effectively what this loop is doing is counting how many values come before the value that we're inserting. And then that's the index that we want to insert at. So at index 1, we're going to insert 5. So we insert 5 there, and anything at or after that index gets shoved down. So this 1 gets shoved down again to index 2. We hit the end of this loop, so we cross it out. Value to compare is no longer in memory. We can't access it. If we want to do output.add location value to compare, we would get a compiler error because that variable is no longer in memory at all, because we hit the closing brace for the block in which it was declared. We signify that in our memory diagrams by crossing out the stack frame, or the code block. And the same thing is about to happen with the other loop. So value to insert and location were both part of this code block. We hit the closing brace of it, so we cross it out. None of those variables are in memory anymore. We only have access to this input and output at this point in time. We're going to return output. So output in the main stack frame got this reference 987, a reference to this array list, which is the same values of the input array list, but in sorted order, in decreasing sorted order. Stack frame ends, so we cross it out. None of this is in memory anymore. None of this is in memory anymore. The only things that exist anymore are sorter, list, and output, which are these 3 references. So these 3 objects. And since the sorter has a reference to this object is also in scope, is also accessible, so it's not garbage. None of this is garbage collected at all, because we can access all 4 objects, and we have 3 variables on the stack. Everything else is gone though. And then finally we print to the screen, and we print our array list. We actually have 4 minutes to spare. I might have rushed at the end a little bit. I'll sit here and wait for questions if there are any. But like this, where we got in the nested loop, things are a little more complicated, but it's concepts that we've seen already. I don't think we've seen actually nested code blocks, so maybe that part was new, but I think it's maybe intuitive, but maybe not. I don't know. That's a tricky one. But a new application of concepts we've seen. So I did go through it a little quick. But any questions? That's my last slide. I want to talk about test 4. There's one thing to highlight. If you're writing your tests and you're trying to submit your tests to Autolab and get feedback on them, you do have to jump ahead to the end of the assignment and write these 3 comparator classes. So if you scroll all the way down here, in these 3 comparator classes, they don't have to be right, but they do have to exist, because my code, when you submit, my code is going to test everything in the submission. So even if these are wrong, that's fine, but they do need to exist, or else my grading code can't compile. If my grading code can't compile, it just can't do anything. So you do have to create these classes with the right setup before you can get feedback on your tests. So I do want to point that out. I obviously have the note right here, but I just want to point that out as many times as I can. Will the quiz be like this memory diagram? I think it'll be more like this one. The quiz is going to feel more like this one. If you're starting for the quiz, do the middle set of slides today. This one I think is a bit too much. We're going to use comparators when we talk about trees on Tuesday. So I want to make sure I get the comparator stuff out there because it does leverage inheritance. So it's part of the inheritance content, but we're going to really use it when we get to trees. And in the homework, of course, as I just pointed out. But the memory diagram for the quiz, for the inheritance quiz or classes 2 quiz, it's going to have more of this style. Mostly because I don't want these invisible constructors, these implicit default constructors that you just have to remember that they exist. I want the constructors to be explicit. So you know that, okay, I call this constructor and then super, maybe you forget what that does at first, but having this line of code here can jog your memory like, oh yeah, there's something there. Oh yeah, Jesse said like 100 times in lecture, superclass constructor call. And then you go to the superclass and call that constructor. I want the quiz to go more like that rather than you get right here and say, wait, there's no constructor. Wait, how does this work again? I don't want you to get bogged down on that. So we'll be creating our own comparator class for the assignment. I didn't see a pre-made class in the project. Yes, you'll create your own comparator, but it can be a cut and paste. You can cut and paste this code right here, or get that from the repo, or type it up, whatever. But the comparator class is exactly this. The only difference is there's no difference in what I just showed, but the only somewhat difference from the repo is that it'll be in a different package. So make sure you get it in the ratings.datastructures package, not in the week 6. I think it's just straight up in the week 6 package. You wouldn't mess with the package. Oh, and there's my lecture over alarm. All right. I'm going to go off stream. I'll take a break and I'll be in office hours if anyone has questions. I'll also be finalizing the quiz grading and posting quiz grades. I'll start that. I'll take a break, start that a little bit, then hop into office hours, answer any questions that are there. And then if need be, if I didn't finish quiz stuff, then I'll finish it after office hours. All right. Take care, everyone. See you Tuesday.